All right, welcome back, SL Physics. Hope that you had a decent break. Here's a topic that we covered about a week before the break, but probably you've forgotten a little bit of it after a long time. We're starting a new topic called waves and oscillations, and this little video is going to be about just reminding us about the stuff that we covered for simple harmonic motion before we left. Okay, so your homework this week is to make sure that you've read pages 146 to 152 in your Tsokos text. All right, the diagram that you have here, or the GIF that you have here, is an example of two different types of oscillations. You have a pendulum moving back and forth about an equilibrium position, and then you have a marble moving back and forth. Now that's not real, that's done by a computer simulation, but they would have to use the same equations that we learn in physics to be able to create that simulation, which is kind of pretty cool. All right, so our first objective today is to be able to understand the conditions under which simple harmonic motion takes place. In life, you see things bouncing back and forth, and you might think that everything is a simple harmonic motion, but objects that are true oscillators have very specific requirements. And one of the requirements is that the system has to have an equilibrium position that it's oscillating about. So for this marble and that bob, the equilibrium position is right over there. There's a driving force that wants that marble and that pendulum to come right back to that point, but because they have inertia, they pass that point, and then they have to keep trying to come back to that point. Okay, so that point right here would be my equilibrium position. Okay, so for example, to explain with a diagram of forces, a free body diagram, why that equilibrium position is there, for example, the pendulum, I can draw the pendulum. Okay, now this object on the bottom is called a bob, okay, of a pendulum, and that's the cord on top of it. Okay, for that object, the force of gravity acting on the bob is equal to the force of tension, and therefore those two forces are under equilibrium, and the object will not move, or it'll move with a constant velocity, according to Newton's first law. Okay, so that's the equilibrium position for the bob. Now, if I pulled that bob away from that equilibrium position, so I'll just draw a new diagram. If I pulled it away, it would look like this. That little dotted line in the middle is my equilibrium position that was there before. Now, the object is no longer in equilibrium because the force of tension is acting in a different vector plane than the force of gravity. Okay, if I draw the vector diagram, force of tension is that way, the force of gravity is that way. The resultant vector here, okay, is going to be acting in that direction, okay? And you can see that that's going to cause the bob to want to come back to the equilibrium position. But when it comes back, it's going to have inertia, and it's going to go past it, causing another situation, or you can flip this to the other side, causing that object to want to come back to the equilibrium position the other way, okay? There's other different types of objects. Any object that has an equilibrium could potentially be an oscillating system. So for example, if I had a piece of styrofoam on water, okay, so here's a piece of styrofoam floating on water, the force of gravity acting on the styrofoam is going to be equal to the buoyant force. That's my equilibrium. But if I push that object a little bit further down, now my buoyant force is going to be greater than the force of gravity, causing the object to oscillate up and down. Okay, so even a styrofoam in water is gonna oscillate. So the important thing is you need to be able to find equilibrium forces and equilibrium positions, okay? So just to give a few more examples, if I have a spring, okay, and I attach a weight on the spring, an equilibrium can be set up because I have a force of gravity acting on the mass attached to the spring, which is going to be equal to the force of tension in the spring. If I pull that mass just a little bit further, I'm going to create a system that's going to oscillate about an equilibrium position because I've given it just a little bit of energy to do that. Okay, and then another final example that a lot of students like to use in their IAs is called a cantilever. Okay, and a cantilever, let's say I had a table and I demonstrated this. On that table, we set up a ruler. Okay, we got it clamped down over here. Okay, that ruler has a force of tension inside of it. Okay, and if I push the ruler down, okay, it's going to bend and it's going to want to oscillate back to its equilibrium position, which is here. Okay, so that's a ruler or a wing on an airplane is going to oscillate up and down. It's going to move about its equilibrium position. So there's lots of different systems that oscillate, but they have to have forces that cause them to want to come back to that equilibrium position. Okay, now that force that wants to bring it back is called a restoring force. Okay, So, whoop. Okay, so a restoring force always tries to bring the moving system back to its equilibrium position. All right, and I demonstrated that before for the bob. Okay, the combination of the force of tension and the force of gravity creates a restoring force. Okay, the restoring force that wants to bring that object back to its equilibrium position. Okay, for a spring, okay, if that was the equilibrium position of the spring, and then I pulled that mass a little bit further down, the restoring force is going to be the extra force of tension in that spring that's going to want to pull it down. Because remember, the force of tension in a spring is equal to kx. Okay, at this point over here, the force of gravity at the point over here, the force of gravity is going to be equal to the force of tension in the spring. But if I pulled it a little further down, I've added a little bit more tension in the spring. When I let it go, now that system is going to want to come back to the equilibrium position. Okay, when it comes back, it's going to have inertia. It's going to go a little bit further, compressing the spring, which is going to move the force in the opposite direction to bring it back to its equilibrium position. Okay, so here are two common examples. For SL, we really look at just pendulums and springs when we're talking about restoring force and analyzing how an object oscillates about an equilibrium position. All right, the next thing that we need to know about oscillating systems is that if it's a true oscillator, the acceleration of the system is always proportional to the displacement of the system from equilibrium, but in the opposite direction. Okay, so for example, for the pendulum over here, okay, if my pendulum is swinging out in that direction, okay, that's what I'm going to call x. My acceleration has to be opposing that motion. Okay, if my pendulum is swinging in that direction, my acceleration is opposing its motion. That's what this relationship is saying. And so true oscillating systems, the acceleration is always opposing the motion of the object, trying to bring it back to the equilibrium position. Okay, and I'm going to try right now to see if we can derive that. And the easiest way to derive that is to look at the motion of a spring. Okay, so if I have a spring and that's my equilibrium position, and I pulled the spring by a displacement of x in the opposite direction. Let's see if we can figure out that the acceleration is proportional to the opposite of, or the acceleration is proportional to the negative of the displacement. Okay, so the restoring force, is going to be equal to the force of tension in the spring, which is equal to k times x. Okay, and that's my restoring force. And then that's going to cause the object to accelerate in the opposite direction. Okay, but my restoring force is negative kx. Okay, so I can even just see right now, if I move m to this side and I'm left with that, okay, now I can see that my acceleration is directly proportional to the displacement, but with that negative sign, it's the negative of the displacement. Okay, and that tells me right now that an oscillating system is going to have that relationship. We'll graph that in another example later on. Okay, and now for the next objective, we need to be able to identify and use concepts of period, frequency, amplitude, displacement, and phase difference. I'm sorry about this little GIF over here. It's the only one that popped up on Giphy, but it'll serve the purpose to be able to describe what we're going to talk about here. Okay, so why does circular motion and simple harmonic motion share language? Okay, in circular motion, we saw the term period, we saw the term frequency, we saw the term amplitude. Okay, we didn't really talk about phase difference yet, but we'll talk about that soon. But it looks like circular motion and simple harmonic motion share some similar terminology. So why is that? Okay, well, that's because objects going in circles also are oscillating about an equilibrium position. I can imagine that I have an equilibrium position right in the middle. Okay, I can see that if I look at it in the form of x, so positive x and negative x, that strange face is oscillating about positive x and negative x. So if I was able to just look at the object on the x plane, okay, I can see it going back and forth on the x plane. Vice versa, okay, I can take a look at the object on the y plane. Okay, so if I look at the object oscillating on across that, okay, I can see that positive y, negative y, yeah, I can see that it's moving back and forth about an equilibrium position right over here as well, okay? So circular motion is oscillating. It's oscillating about the x-axis and the y-axis, okay? And we have a lot of understanding of these terminologies. Period is the time that it would take to complete one full cycle. So if I started here, it would be the time that it would take to come back to that point. That's the period, okay? And the frequency is how many cycles that face is going to make per second. So in this case, it looks like it's around 1 hertz. And that's something we've learned already. Okay, the amplitude is the maximum displacement from that equilibrium position here. So that's my amplitude, the maximum displacement. Okay, and my displacement at any moment, now this is in the y-axis, okay, so it's getting farther, now it's at its amplitude, now it's getting closer to the origin. Okay, my displacement is from the equilibrium position. Okay, so those are important terms that we can use to define and describe where an object is and how fast it's moving when we're looking at simple harmonic motion. Okay, so we understand that the terms period, frequency, and amplitude and displacement share the common language of circular motion, and that's basically what I wanted to cover in this first little video. Okay, you have to be able to define that. But the last part, where we're talking about phase difference, is when I'm looking at two different objects that are oscillating and looking at comparing at where they are in their oscillation. So if I take a look at this little GIF I have of two oscillating systems, okay, so this first, an oscillating, it doesn't look like, it's a really strange graph, but just imagine that is an object going into a circle, okay? And what we can see when we have phase difference is that one oscillator is at a different point in its cycle than the other oscillator. And if they're at the same point, they have zero phase difference. If they're at opposite ends of the spectrum, then they are out of sync, okay? And we'll be talking about that a little bit more when we start graphing, how to describe systems when they're out of sync, okay? How far are they out of sync? Is it easier to describe in terms of amplitude, or can we describe it in terms of angle? Okay, and so what we can see here is oscillator 1 seems like it's a little behind oscillator 2, and if I was to graph it in terms of angle, you can see that the sine graphs are not overlapping, they're kind of off from each other. Okay, well that's it for the first little episode. Next time we're going to talk about graphing. All right.